Hi guys, welcome to my follow-up lecture on thermal conductivity, and today we'll be looking at the method to determine thermal conductivity of poor conductors or bad conductors according to the Lee's method. Alright, so basically we are going to have this setup here, so I'm going to explain it. And in the first diagram, you basically have a brass disc at B here, and you are suspending it with a thin wire, and you are placing a sample of poor conductor, which is the green slab. It has a very large cross-sectional area to allow the heat, because remember, it's not a very good conductor, so you want it to be very wide, large cross-sectional area, capital A, and a very thin thickness, common A, which represents delta X. Now on top of this, you're placing a steam chest, and the base of the steam chest, which is the blue diagram, the base of the steam chest is also a brass material. And embedded in the two brass discs, the one at the bottom C of the steam chest, you have a thermometer T1, and in the other one you have another thermometer which measures the temperature θ2, T2. Right? Now we are using the equation as we saw in the previous video. K is equal to Q over T, right, which is your heat flow, rate of heat flow, over your cross-sectional area by your change in temperature over thickness, right? So the first thing we have to do is we have to get your cross-sectional area A, which is of your disk, which is pi d squared on 4, and you use your normal instrument to measure that. And then of course, to get your temperature delta theta, it will be the temperature difference across θ1 and θ2, and the thickness will be common A. Right, so basically we are using another method I'll explain just now to find Q on T, but you are measuring A from the sample. It's a circular disc. You would have the cross-sectional area capital A being pi the diameter squared over 4. You are using your temperatures of thermometers T1 and T2 to get delta theta, and then of course you have the thickness A is equal to delta X. So the first thing you would need to do is you would need to use your steam chest. You're placing it on the sample, and you are allowing it to transfer heat from C all the way to B, and of course this would occur until you have a steady state being attained. When steady state is being attained, you are maintaining a constant temperature difference across thermometers T1 and T2, right? And when steady state is attained, the rate of heat flow through the base of the steam chest and all the way to brass disc B is the same. And then you are assuming that heat will then escape from the bottom of disc B. So now to determine, right, so we're using the first setup to determine what K is based on A delta theta delta X, right? So we would have set up the apparatus. We would allow our brass disc B to be suspended in air using fine wires. On top of this brass disc B, we're going to place a sample of the poor conductor. The sample is thin to allow a temperature gradient to be very large, and the cross-sectional area is also large, and that is to maximize the efficiency of heat transfer because it's a poor conductor. You are ignoring heat loss from the sides. Steam is then passed from the steam chest, and when steady state is attained, θ1 and θ2 are noted. So when steady state is attained, the rate of heat flow through the base of the steam chest C and the top of the brass disc B are the same. Alright, so based on that, we would have acquired A. Remember, we're going to let A be pi d squared over 4. We would have had delta theta and delta X, which is A. Right? So now we are going to determine Q on T. So we're going to kind of change up the apparatus a little bit. So now we're taking out the steam chest and we just leaving brass disc B. So we're taking out the sample and the steam chest first. And remember, this represents θ2 from thermometer 2. Alright? So you're taking off the sample and the steam chest, and you're going to heat the brass disc B until the temperature is a few degrees above your θ2. Right? Then you're going to put the sample on top of it, and then you're going to let B be cooled, because you want to determine the rate of heat transfer of B. Remember, at steady state, the assumption was that disk B is providing heat, right, at the same rate as disk C. That is what steady state understands. So now you are going to measure what is the rate at which disk B is emitting heat energy. So you have heated it, so you take off everything, steam just and sample, and then you heat it using a Bunsen burner. It remains suspended using a thin wire, and you heat the bottom of disk B until it attains a temperature a little higher than theta 2, right? Because you want to now find the rate at which at that theta 2 temperature it emits heat, right? So then now after it raises a little bit above, because remember you're assuming that there are some heat losses through convection currents because it's not taking place in a vacuum, and then you place now the sample on top of it. So when you place the sample on top of it, you allow it to cool, and then now you allow theta 2 to fall until the reading of theta 2 is recorded every half a minute until the temperature is a few degrees, right? Until temperature theta 2 falls by a few degrees, right? So you're going to allow it to become heated until the temperature is allowed to fall by a few degrees. So now you are going to do your graph of theta versus time, and you're going to look at theta 2, and you're going to do a tangent for me. So when you do a tangent here, you're going to let it extend a couple of degrees above and below theta 2, and this represents delta theta over delta t. So you're going to draw a tangent through the point of theta 2 on your curve, because remember you're assuming it's a poor conductor and you are not having any uniform rate of heat loss, okay? So now we are going to say that Q over T is equal to MC. This is the mass of disk B. This is the specific heat capacity of brass. And then you're going to use your tangent to get delta theta over delta T. So now that you've gotten that, you let MC delta theta, so all of this is your brass measurements, be equal now to Ka by theta 2 minus theta 1 all over A, and you solve for K.